So we continue session 2 for lecture 6. And we will talk about an example. We will give an example of how to make the multiplication of the example on the screen. Of course, to do that, we need handwriting. So I will share my screen. I will share my camera. So this way I will share my camera. Okay, I think this is my camera.
دكتور إذا بتعطيهم دقيقة شوي.
Okay.
دكتور نعطي.
So here we take an example. I will show you the printed slides because I just want to write down. I will not be able to write all of these matrices, so it is better to have it in front of us. So, for example, I want to multiply. I found a simple way better than taking GF of 2 to the power 8. I found it with a better way to do that. I will tell you how to make this multiplication. So I take the first row.
دكتور مو بلازم نعرف صح كيف؟
ها؟
مو بلازم نعرف صح؟
No. You have to know. If I explain it, you have to know it. Multiplication is like to how this 9-5 is moved to be 2a. How the 9-5 is moved to be 2a. Okay. It's important. I will tell you how to do that. It's very simple. I found a very simple way. It's better to use the polynomials. It's better than polynomial, not to use polynomial. It's better than polynomial. You don't need to do any polynomial multiplication. It is just a simple XOR. So, and a normal multiplication matrices. So, for example, I take this one and I multiply it by that one. I do it like that. 1, 0, 0, 0, 1, 1, 1, 1. I take that one. And then that one, I take it and put it behind that one. So I take 0, 1, 0, 1, 0, 0, 0, 1. Then the result of this operation should be 1. The result should be 1. Okay? How this is coming? This is just a normal multiplication. Normal multiplication means this is 1 by 1. Normal multiplication, just like decimal multiplication. So 1 by 1 is 1, 1 by 0 is 0, 0, 0, 0, 0, 0, 0. And then XOR all of these. How to make the XOR operation? The result here, how many ones here? How many ones? If the number of ones is odd, so the result is 1. If the number of ones is even, the result is 0. Okay, this is very simple. I found this way is very simple, better than the polynomial multiplication. So again, I want to multiply this one by that one, and the result should be 1. I do it by multiplications, just normal multiplication. So 1 by 1 is 1, 1 by 0 is 0, and so on until I get the ones and zeros here. And then count how many ones inside this output. If it is odd, the result should be 1. If it is even, the result should be 0. And that's very simple. I can continue doing the second one, which is 1, 1, this one. 1, 1, 0, 0, 0, 1, 1, 1. And then I multiply it by the same column here, which is 0, 1, 0, 1, 0, 0, 0, 1, right? Okay, and then multiply, which is 1. The result is 1, 0, 0, 0, 0, 0, 1, 0. This way, which is not odd, it is even. This means the result is 0, not 1. Here the result is 1. Here the result is 0 because the number of ones are 2. 2. 2 is even. Then the result should be 0. So I take 0 and put it here in the result, which is here. I can do all of these operations, and then the result should be, this is fixed. These two are fixed. Don't think about them. Don't worry about them. They are fixed in the algorithm. You worry about how to get that one, and how to get the result. And the result is very simple, XOR. 1 XOR 1 is 0, 0 XOR 1 is 1, 0 XOR 0 is 0, 1 XOR 0 is 1, and so on. Now I get this one and I put it in the reverse order, as I told you. This is from 0 here, 0, 0, 1, 0, and then 1, 0, 1, 0. 0, 0, 1, 0 is 2, and this one is A, which is 10. So the result should be 2A. Okay? You understand it? You understand?
Yes, doctor.
Okay. It's very simple. It's better than making polynomial multiplication. And then we move to share our slides back.
دكتور
Yes.
اوكي فاين خلاص
في سؤال يا نورهان.
دكتور مش عارفة، حاسة ان انا اتلخبطت او انا عرفت ازاي multiplication already بتتعمل تمام، بس اللي هو third column، الكولوم الثالث جت ازاي الريزلت اللي هو يعني اول حاجة وتاني حاجة عرفناها الجدول اللي موجود تمام.
This one.
يس بعدين اللي هو ال 95 I think اللي هو second column.
95 is converted to 8A. You know from where?
Yes, doctor. Okay, to 8A. So 8A and first table, the matrix, the first one is okay. Then after the XOR sign, how it comes? I understood about the even and odd. But how the numbers came, يعني...
Which number? This one?
Yes.
This is, I told you about the number of ones and zeros. The result has number of ones and zeros. For example, if I multiply 1 by 0, it's going to give me 0. 0 by 1 is 0, and so on. I found one, or I count how many how many ones are there in the result. For example,
it's odd. It was odd.
It was odd, so the result is 1. If it is even, the result is 0.
Okay.
This is very simple. Yes.
Yeah.
You count, this is an XOR operation, but on multiple ones. For example, if you have just one and the others are zeros, so the result should be 1. If you have 1, 1, 1, 1, for example, you XOR the 4 ones, you will find the result is 0 because the number of ones are even.
Okay, Doc. Okay, thank you.
Okay. So this way, we understand right now that how to get the inverse, the S box here, and the operation of getting inverse S box is to the right hand side. So now we know that S box and the inverse S box are not created randomly, and instead they are created by a specific multiplication, just to make sure that the operation. Okay, Saif, you reminded me at the end of lecture. So the S box operation and the inverse S box operations are done by this algorithm, and we understand simply one example. And here Why S-box? Why we do S-box? Actually, S-box is designed to be resistant to any known cryptographic analytic or attack. And also the developer of this is Regendal. Regendal is a scientist who developed the idea of S-box, sought a design that has a low correlation between input bits and the output bits, and the probability that the output is not a linear mathematical function of the input. As you know about linear functions, linear functions means that we can go forward and go backward. If it is linear, we can go forward and go backward directly. We calculate, for example, if the function is y and x, you can get x from y, and also you can get y from x. This is because it's linear function. But if it is not linear function, if it is in the multi-dimensional space, this is going to give us a very complicated function that is not reversible. This is not that is not easily reversible for the attackers. Unless they know the internal structure of the algorithm. Without knowing the internal structure of the algorithm, they will not be able to create or get the plain text from the encrypted text. What is the linear operation? Maybe I can give you an example about the linear and non-linear, because it is important. You will find many algorithms say linear mathematical for a function. For example, if I have y plus 2 equal x plus 0 or plus 1, this is a linear operation. I can calculate y given x, and I can calculate x given y. For example, I can get y as a function of x. So it is going to be x. So to move to the right-hand side by minus, so x minus 1. And also I can get x given y. So I can get x equal, I move 1 to the left-hand side, so it's going to be y plus 1. Now I can get x given y and y given x. This is the concept of linear operation. But what about if I tell you something like that? X cubed plus y cubed plus 2 equals 0. Can we get, let me clean this by eraser. Clean. Okay. Here we concentrate on the x cubed plus y cubed plus 2 equals 0. Can we simply get x given y and y given x? Can we do that? Can you do that? Do you know how to do that? You can actually, but it is little complicated. It is little complicated because we are not linear. We are not having linear equation. We have an equation to the power 3 in 2-dimensional. Or you can say 1 dimension, not 2 dimension. Actually, it is on 1 dimension. So this is an example of non-linear operation. Non-linear. This is linear operation. To the right-hand side is linear operation. To the left, x cubed plus y cubed plus 2 equals 0. This is non-linear mathematical operation. We cannot easily take x from y or get x given y or y given x. Allah Akbar, Allah. Can we stop for a moment for the azan? Just to stop because
Yes, doctor, of course.
Inshallah. Okay, we continue back the non-linearity and linearity, or the linear mathematical function and non-linear function. I told you about the linearity means that I can easily get the output from the input and the input from the output, but for the non-linear functions, this is not possible, or this is very difficult. We can say this is very difficult. Okay, so we have finished the first of operation. To remind you by the stages, we can say stages is better than operations. We can say stages. Here we have 4 stages. The substitute bytes, and we know how to make substitution using the S box and the inverse S box. And the second stage is shift rows. The third one is mix column, and last one is add round key. We finished already. We finished the substitute bytes, and then we move to the shift rows. We move now to the shift rows, which is here. This one is shift rows. And the shift rows, as you see, we have here column by column data, and then the shift is moving the byte from column to column. It's like shifting it from column to column. So, for example, the first row is not changed. No change in the first row. In the second row, we shift left. So if the byte as the left-hand side, I move it to the, if it is to the right-hand side, I move it to left, to the right, to the left, to the right, to the left, and then the last one is moved to the first byte. And here we jump, this is jump 1 by 1 byte, 1 byte by 1 byte. This is jump 2 bytes. So for example, I shift not to the neighbor byte, to the after the neighbor byte. And here, these two to the right is shifted to the left, and this two to the left is shifted to the right. And the last one is instead is like the first one. Instead of shifting to the left, we shift to the right. Okay. And here we can see an example. I can make like a notation to make you understand. This is no change. The first row has no change, actually. No change in the first row. For the second row, I see that 90 is moved here, and 4C is moved here, and 6E is moved here. 90 is moved here like that, and 4C is moved to here, and 6E is moved to. So where is EC? EC is moved to instead of 90. Okay, EC. What about the second one? We have 2 bytes here. We move them to the right. So 4A and C3 is moved to the right, and 46 and E7 is moved to the left. And the last one is shifting to the right. Instead of shifting to the left in the second row, we in the third row shift to the right hand side. So 8C should be here, and D8 should be here, and A6, where is A6? We have to move it to the instead of 8C. So A6 is moved to here at the beginning, and 9-5 is moved to here. Okay, is it clear? Is it clear? No problem. I think this is very straightforward, no problem in it, right? Okay. You have any problem? Okay. No problem. Okay. So let's move to the third stage, which is mixed column. Mixed column is the same operation as we said about the construction of S box. It contains multiplication. It contains mathematics. It contains mathematics. I take the input box here, which is coming from the third. We are in the third stage here. This is the second stage. The first stage is S box. This is the second stage, which is shift rows, and this is the third stage, which is mixed column. This is the mixed column stage. The third one is simply we get this matrix. This matrix is fixed, as I told you about that one with the S box and the inverse S box. This is fixed. If you want to know more about them, you can refer to the text box. Even the text box may refer you to some references. Maybe not explaining it, but he can tell you about some references. You can get why we use exactly this one. This matrix is fixed. We have here the input, we put it here, and then we make multiplication. And this multiplication is not simple XOR. As we said before, this is polynomial multiplication. I will give you a detailed example after a while. But you know now, I put the input text here, the input data here, and we have this matrix, the mixed column matrix, and then make multiplication and to get this result. So we have input here, we put it beside the mixed column matrix and then make multiplication, then the result is here. Okay. Let's move to, I will tell you a detailed example of how to make an example of mixed column. So why shift rows? Actually, shift rows is scrambling the data, so we make the probability of getting an output in each bit is equal to 0.5. This means we make the data totally random. We make a totally random data. The output should be totally random, or pure random, means that each bit should be either 0 or 1 with the probability of 0.5 for both of them. That's why we make a shift row. So maybe you see it is very simple. We shift rows from left to right or from right to left, but it is very strong way to get the scrambling or to get the diffusion operation that we need in each encryption algorithm. On encryption, the first 4 bytes of the plain text are copied to the first column of the state. The round key is applied to the state column by column. He is explaining how to make these operations. The 4 bytes of the plain text are copied to the first column of the state. This means that the addition of the key is done column by column. Okay, and the transformation ensures that the 4 bytes of one column are spread out to 4 different columns. This means this transformation or shift rows means that the data, the effective data, is moved from one column to the other. So each input data has an effect on the output. Each input data has an effect on the output, and this is ensured the diffusion property, which is I change single bit in the input, I get a totally different output. This is shift row. Shift row, maybe you see it is very simple, but it is very effective. Let's move to the most difficult part in this lecture, which is mixed columns. Mixed column, the coefficient of mixed columns makes sure that the maximal distance between code words, and that ensures a good mixing among the bytes of each column. Why that? This means that we make like making let's return back. This matrix which contains 0, 2, 0, 3, 0, 1, this matrix ensures that we have the largest distance between each byte. This means that we cut the relationship between the internal structure of the byte itself. For example, I will tell you something. For example, if I have the byte like ordered like 1, 2, 3, 4. You know, this is very expected. This is you know, the relationship between them is very straightforward. If I miss the 4, I can get it because I know that 1 after 1 is 2, after 2 is 3, and of course if I don't have 4, I can guess it. And the mixed column is like getting here, this, which is the maximum distance between these 2 bytes, which we can say that 1 and 4 has the maximum distance, so I put them together. So 1, 4 like that. Because I put the next one with the maximum distance. 4, what about 4? We have 4 and the remaining one is 2 and 3. So 2 or 3, I put 2 or 3, I put 2 because 3 has distance of 1, but 2 has distance of 2. And the last one is 3. So this is the input and this is the output. It's like scrambling the input data. There is some kind of relationship in the input. I cut this relationship. I confuse the input. I scramble it, so no way. There is no relationship internally inside each byte. Okay, you understand why we use mixed columns? So if we have in the byte itself, if we have a relationship between bits, I change it. I cut this relationship. For example, if I have all the first byte has all zeros at the beginning and all ones at the end. I change all of these. I make it, for example, 0, 1, 0, 1, 0, 1, something like that. So I cut the relationship inside the byte itself. That's why we use a mixed columns. Now we move to the add round key. The add round key. We have 108 bits of state, and then this 100 bits of state is XORed with the input round key. The input round key. So it is a column-wise operation between the 4 byte of a state column and the word of the round key. As I told you, the column-wise operation, as you see here, we have to return to this figure because it's important. Maybe it's the second or third. Yes, this one. So we have here the key, the input key, and we have word by word. We have 44 words here. And each one of the 44 words is added to one column of the input data. It is XORed with it. So this W0 is XORed with S00 together with S10, S20, S30. And for the word 1 is combined or XORed with S01, 11, 21, and S31. And so on. This continues until the end of the entire data. This, of course, this is the state of each round. You know, this is the output of each round. The output of each round. Let's move to the so the rationale or why is that is simple as possible, affects every bit of the state. This means each output state of each round, we have the effect of the key. So the key has its effect. If we change the key or a simple bit of a key, we get a totally different output also. The complexity of the round key expansion plus the complexity of the other stages of AES ensure security. This means we cut the relationship between the input and the output. Given the output, the hacker will not be able to get the input. And here the general structure of the AES round. This is a very simple way of representing the AES structure. The first stage here is a sub-byte. This is one round. The entire drawing is one round. We have the state matrix. The state matrix is moved to the sub-bytes, and we need the S box in that sub-byte, and then the output is moved to the state matrix, and you know that the state matrix is important because we are going to use it here. We are going to use in the round key and shift rows, and you know about shift rows, how to make it, and then state again, and then mix column. We need this matrix as input. If we don't know this, we will not be able to make the mix column operation. This is an input to the algorithm. And the last one is add round key. And we take the round key. The round key is one of the 44 subkeys. And then we make simple XOR operation to get the last state matrix. These are constants, and this is variable. This is constants means, these are constants means they are not changed. S box is not changed actually. And the mixed column matrix is not also changed. This is fixed structure. But for the round key is different because the key will be different for each input. And this is one round, the internal structure of one round. Okay, let me have you wake up with me. Can anybody tell me about the subbytes? What is the subbytes? Can anybody tell me very quickly what is subbytes? How to make it? How to make this operation? Nobody knows? Nobody's here?
Yes, doctor, we are here.
Okay, that's good. Using Nurhan is not willing to say anything, but she write on the chat. That's good, Nurhan. Using SBox and inverse SBox. That's good. But how to do that? How to make it? Okay. Okay. Okay, let me say it. Let me say it. This is simply we take the input byte here and we go to the index of the S box. For example, the index is divided to 2 bytes. For example, 2A. So I go to the row number 2 and the column number A, and they get the corresponding byte and then put it here. Replace it or substitute it. This is the S bytes. Okay, anybody tell me about shift rows? This is simple. Shift rows, how to make this stage.
Doctor, by shifting bytes left or right?
By shifting again?
By shifting bytes?
Yeah, shifting by Haneen, yes, you are right. By shifting bytes from right to left or from left to right. And anybody tell me why we use subbytes? Why it is important? Column by column shift. That's right, Nurhan. Nurhan, that's right. What about the subbytes? Can anybody tell me why we use subbytes? Why it is important? Why it is important? Why subbytes are important? Why we use all of these scrambling, shifting left, shifting to the right, S box substitution, and all of these operations? Why we use them? Why they are important? We are scrambling the data. It's like you have a collection of letters and you are scrambling them. Scrambling them means that you just lose their arrangement. Like the scrambling of the cube. There is famous cube, is called what? I forget the name of that cube, which has colors for each side, and you have to order the cube so one color at each side. It's like that. So scrambling it means that you have already the cube is ordered or arranged, and then you scrambling it. Scrambling it means you change its order. Okay, you don't know? Anybody knows why we use subbytes, shift rows, mixed column, all of these stages? Why it is important? Why we have the headache of doing all these complications? Yes, Nurhan, yes, you're right. We to encrypt the data, but we can encrypt it simply by Caesar cipher, for example. Why we use complicated operations? Okay, let me answer this one. We have two main properties for each encryption algorithm. The first one is confusion, and the second one is diffusion. Confusion means I cut the relationship between the input and the output. I'm doing all of this scrambling and shifting and multiplication, or all of these operations to make sure that there is no relation between the output and the input. This is the first one. The second one is the confusion, or the diffusion, sorry. I said about the confusion. The diffusion. Diffusion means if I change a single bit in the input, it will totally change the output, or the avalanche effect, if you know about avalanche effect. If I change just a simple bit in the beginning or the input, I will get totally different output. These two properties must be existing in all encryption algorithms. That's why we use subbytes, shift rows, mixed columns, add round key, and also the key is not used directly. We have to make the expansion algorithm. I will talk about the expansion algorithm right now. This one. Here we have the key, the input key. Here we have the input key, and the input key has these 4 words, and the last word contains an operation called G, and if you also the fixed one, I don't want you to get into the detail how this operation is done, but anyway, the first word, for example, the first word is moved directly to the first word in the output, but actually is not true. It's not moved directly because we have XOR operation here. XOR operation is done with the output from this G. And the output from this G is taken the W3, only W3, not all of the bytes, just W3. So W3 is done, function is applied on W3, and the output is XORed with W0 to get W4. W4 is XORed with the output from W1 directly to get W5. W5 is XORed with W2 to get W6. W6 is XORed with W3 to get W7. And this operation is continued to the last round. What about the function G? The function G is here, expanded here. This is the function G. We have a word here, and this word is moved to 4 bytes. One word is 4 bytes, so it is 4 bytes, and this 4 bytes is rotated or shifted right and left. For example, B0 is moved to B0 to the right, and B1 is moved here, and B2 is moved here, and B3 is just scrambling the word, and then applies the S box operation to B1 and B2, B3, B0, and the output is here after S box substitution. And also we XOR by RJ, which is the constant or round constant. RJ is abbreviation for round constant. And this round constant is given to the algorithm. You can give any constant to the algorithm. And then XOR the result from here, from the S box after the S box operation to get the W dash. This is just zooming out G, zooming out for G, okay? And that's the expansion operation. After the expansion, we get a 44 bytes or 23 bits. 23 bits. This is the subkeys. And also Regendal, which is who developed all these algorithms, designed the expansion key to be resistant to any non-cryptographic or cryptanalytic attack. So he think about how to protect the algorithm using the key. The key is important, as you know. If somebody knows the key, he will be able to get the data. And also the inclusion of round-dependent round constant eliminates the symmetry between the ways in which round keys are generated in different rounds. This means that the key, you know, the key is just a very simple word. For example, I can make a password like my name, for example. I put my name as a password. This is the key. And the key has internal relationship between its bytes. The key expansion relation or the key expansion algorithm makes sure that this relationship inside each byte is cut. There is no relationship between each part inside the key itself. Okay, and that's why we use and also these specific criteria Regendal used. For example, knowledge of a part of a cipher key or round key doesn't enable the calculation of many other round keys. This means if I know some of the subkeys, I will not be able to construct the key itself. An invertible transformation means I can do forward and I can do backward, forward and backward, going and back, and so on. This operation is reversible. Speed on a wide range of processors, because some of the algorithms are implemented by hardware. So here Regendal makes sure that it is of high speed, this operation, which is the construction of or the expansion of algorithm with a high speed, to make sure if anybody wants to make it as hardware, he can do it as a hardware. And use of round constant to eliminate symmetries. This is the round constant RC. RC is used to remove any symmetry in the data. Okay, so you can continue reading others. Okay. And here we get to the real world example. This is an example, but this is a key expansion example. This is a key expansion example. We have here W0, which is the input, and after the rotation or the first, we have here the first three operations, subword and rootward is rotation, and this one reconstruction. Word 3, W3. Oh yes, this is the internal structure of the expansion key here. That's that one. The expansion key is explained in these operations. Okay, so this is, I want you to concentrate more on the next slide, this one. Okay, This one is more important because I want you to know how the AES operations are done. After subbytes, in subbytes, and for the shift rows and for the mixed columns. Okay, so I give you an example. I give you a detailed example, but I don't know how to do that right now. Okay, but I have an idea. I have an idea. Okay, I can. Okay, I can take this and I can print out. I can print out this one. This one. This slide. The full slide, I printed just one slide, which is the current slide. Print current slide, and then print this slide. I print out the slide, and then show you how to make the calculations. Okay. And I think I need only the table, so I cut that piece. No need for it. Okay, let's leave it for now. Let's leave it and then make our operations. Okay, so I share my screen to tell you how the operations are done. Here I share my screen, my camera. Camera is here. And here we go, this one. Okay, I think we have to switch it like that. Okay, concentrate, please. This is very important. This is encryption is all about calculations. It's all about calculation, mathematics and calculations. So make sure that you understand the stages here. The first one is the round key. Here we have, for example, I take 0f. I think you see it. Okay, let me return the lamp back. Okay, that's good. Okay, here we have 0f. Here is a round key. I take the round key and XOR it at the beginning. We have input. This is the input. This is the input text. I want to encrypt this input text. And this is the round key. Round key means a sub key. Sub key. Okay. We created this round key. In each round, we have 44. If you count those, you will find them 44 sub keys. Okay. But I think they are not covered with the 44. This is an example. So we have 0f and 1, 0f and 01. Here, the first one is making the add round key. The add round key is just a simple XOR operation. So if I get this one is 0f, which is 0, 0, 0, 0, 1, 1, 1, 1, and then XOR it with 0, 1. So 0 and 1. I convert from binary to hexadecimal. And then XOR operation means this is 0, this is 1, 1, 1, 0, 0, 0, 0. If you see this is 0, and this is what? This is E. This is E. Okay? This is you have to know how to convert from binary to hexadecimal. From binary to hexadecimal. This is E. So we have 0E. So I take this 0E and the output, I put it here, 0E. Okay? So this is 0E. I can repeat the operation. I can take that one XOR with that one to get CE. 0C with FE to get F2, and so on. Okay? Do you understand the add round key? Add round key is simple XOR operation. Okay, so we finished add round key. We take 0E, that 0E, and then 0E, and we make sub bytes. Okay, sub bytes using SBox. So the first stage is adding add round keys, and for the sub bytes I take 0E and show or see where is in the SBox is 0E. I go to the SBox. Let me bring it. This one. 0E. I want 0E, so I go to 0E here. I think you can see it. 0E, 0E, this one, which is AB. 0E is AB. So I replace 0E by AB. So the output is AB. I put the AB here after the sub bytes. I can also repeat all of these operations. So I go to CE. I go to CE here. CE. 8B. I take 8B and put it here. 8B. All these can be done this way. Sorry, 8B here. They are the same. I will tell you why. So 8B. And for the F2, I can repeat it again to if you don't understand. F2, 8, 9. F2 is 8, 9. So I put 8, 9 here. I take F2, replace it with F9. 8, 9, sorry. F2 is replaced with 8, 9. And so on. You can continue this operation to finish all of this. No problem. Now you understand the operation. After the S bytes, I make shift rows. Shift rows is simple. You can see here the first row is not changed. The second row is shifted to the left, means 40 will be here, and 7F will be here, 7F. And F1 is here, and 0F is moved to the first. You can continue the same operation here. These two is moved to the right, and these two is moved to the left. And right shift, which is E4, is moved to this place. 4E is moved to this place, and 2F is moved to this place, and the C4, which is this one, is moved to the beginning.
دكتور الشفت نحن كم يعني كيف نعرف الشفت ولا دوم هل مثلا اثنين نحرك يمين؟
الشفت معروف معروف في الالجوريثم. The shift is well known in the algorithm. The first row is not shifted. The first row is no shift. The second row is left shift. The third row is just to swap the right hand side and the right hand side and left hand side parts. And the last one is shift right, move right, shift right. This is you have to keep it in your mind. It is fixed. You cannot do it randomly. It's fixed. Now, after the shift, this is the result. This is the result of the shift. Okay, now we concentrate back on our AB. We go to the AB. Now, how to get the B9 from AB? This is the most important, most difficult part. You just concentrate with me, and then you will find it not that difficult. Okay? Okay. Let me take Now I have this AB. How I get B9 after mixed column? You remember the output, which is B9. I want to get B9. I don't know how to get AB, take AB and then get B9. I will tell you the operation in detail right now. I think this space is okay. I can use it. I can use this space, no problem. Okay, let's take it like that. We have here the mixed column matrix. Mixed column matrix is fixed. This is fixed, 0, 3, 0, 3, and 0, 1, 0, 1. And here 0, 1, 0, 2, 0, 3, 0, 1. And this one is 0, 1, 0, 1, 0, 2, 0, 3, 0, 3, 0, 1, 0, 1, 0, 2. I multiply it by the input, which is after the shift, which is this matrix. This matrix. After the shift row, I get this matrix, I put it here, AB and 8B. Okay, I know the others, I can take them from here, 8B and 8, 9, and then 3, 5, and then 4, 0, then 7F, then F1, then 0, 5, then F0, FC, 1, 8, the 3F, C4, E4, 4E, 2F. Okay? This is the output here, exactly the same here after the shift row. 2F, last one is 2F. Here is 2F, here is 2F. Here is 3, 5, here is 3, 5. I copy this one here, okay? Now, I make the multiplication, just a simple multiplication, not that simple, but I have to change all of these. I want to get just only this one, this cell, one number, and then the remainder will be the same. The remaining operations will be the same. How to make this multiplication is simply to change all of these to polynomial. Change all of these to polynomial. So the multiplication should be like that, 0, 2 multiplied by AB, 0, 2 multiplied by AB, plus 0, 3 multiplied by 4, 0, plus 0, 1 multiplied by F0, plus 0, 1 multiplied by C4. This is the operation. But this operation is not done like that. I have to make it with GF multiplication or polynomial multiplication. So 0, 2, I can know how to make it like, okay, let me take it like that. We have 8 places. For each byte, we have 8 places. This is 1, this is x squared, this is x cubed, this is x4, this is x5, x1, x4, x4, x3, x4, 0, 1, 2, 1, 2, 3, 4, 5, 6, 7. Okay, now this is 0, 2. 0, 2 means it is here, only here, 1 here. This is binary representation of 0, 2. The binary representation of 0, 2 is 1, 0, and the others are 0. So it is x. So I multiply x by what? By AB. I have to convert AB to the corresponding binary number. I have to convert AB to the corresponding number, so I can say A is 10, like 1010, 1 0 1 0, and B is 1 0 1 1, right? 1 0 1 0 is A, and 1 0 1 1 is B. So this way the polynomial is x to the power 7 plus x to the power 5 plus x to the power 3 plus x to the power plus x only, there is no power, plus 1. So it is x7, x5, x3, x1. Okay? You know how to get this? This is simply AB. AB is represented in binary here, and then you get the corresponding power, the corresponding x to the power. So for example, this is 1, so I get x7. This is 0, I don't get x6 because I don't, it is 0 here. 1 multiplied by x7 plus 1 multiplied by x5 plus 1 multiplied by x3 plus 1 multiplied by x plus 1 multiplied by 1. And the result, I put it here. Okay, what about the second one, which is 0 3? 0 3 means I have 3 is 1 1, which is x plus 1. This is x plus 1 multiplied by the 4 0. 4 0 means I have 4 here. 4 is 0 0 1 0. So 0 0, this is 1, this is 2, this is 4. 0 0 1 0. This is x6. So it is only x6. It's only x6. So x plus 1 multiplied by x to the power 6 plus, I finished those two. 0 1. 0 1 is very simple because it is 1 multiplied by f0. f0 means we have 4 1s here and 4 zeros here. So we have x7 plus x6 plus x5 plus x4. So we finished this one. The last one is 0 1 c4. 0 1 is 1 multiplied by c4. I can see A, B, C. So A is 1 0 1 0, B is 1 0 1 1, 1 0 1 1, right? And the C is adding 1 to these. So adding 1 is like 0 0 0 1 1. Sorry, 0 0 1 1. This is C, should be C. Because the A is 10, 11, 12. Make sure if this is 12. This is 12, yes. This is 4 plus 8. This is 4 plus 8, which is 12. So this is C. This means C and 4. So it is C, 1, 1, 0, 0, and 4, which is 0, 1, 0, 0. So this is x7, x7 and x6 and x2. Okay, this should be done like that. Okay, let me simplify it. So we have here, I have to simplify this operation. How to simplify it? I can take x multiplied by this one, which is x to the power 8 plus x to the power 6 plus x to the power 4 plus x to the power 2 plus x. I multiply x by this one plus x to the power 6 is multiplied here, so x to the power 7 plus x to the power 6 plus here x to the power 7 plus x to the power 6 plus x to the power 5 plus x to the power 4 plus x to the power 7 plus x to the power 8, sorry, this is 6 plus x to the power 2. Now we count how many odd and even numbers. For example, I have only one x8, so the result should be x8. What about the 7? How many 7s are there? 1, 2, 3. 1, 2, 3. So x7 is with us because it is odd number. I mean, it appeared 3 times. So it is odd number, so it must be appearing because XOR, I remind you by XOR, if it has odd number, so it is 1 or existing. If it is even number, so it is not existing or 0. So x7 with us. x7 with us. x6, we have how many x6? 1, 2, 3, 4. x6 is not with us. What about x5? x5, 1, only one x5, so it is going to be with us, x5. What about x4? We have x4 here and x4 here. We're not included with us. x3, there is no x3. x3 is not there. x4, x2, x2 is appearing here and here. So is even number, so is not included with us. X, only one x. So there is no other x, only one x, so it appearing with us. Okay. Now the last one is 1. I think we don't have ones, so it's okay now. So the result is this one. We have here the last bit is 1, so we have to make this x8 means that we have the most significant bit is 1. This means we have to make long hand division. I make long hand division with the irreducible polynomial. I told you about it. We put that one here, x8 plus x7 plus x5 plus x. And then put the irreducible polynomial. The irreducible polynomial, I remind you by it, which is x8 plus x4 plus x3 plus x plus 1. So I use 1 here. I multiply these two together, so it is going to be x8, x4. So you can use add x3 plus x plus 1. XOR operation. So x8 is going to be reduced with x8. x7 is with us, x7. And x5 and x4 and x3 and 1.
دكتور هني division مال XR نسوي؟
Yes, this is XOR operation. So I divide that one by that, so I get 1. 1 because the last power is 8, so I just need 1. So I multiplied 1 by this one and then get the result here. I put that here only. Then XOR operation means if they are similar, I remove them. If they are not similar, for example, x7 is appearing here, not appearing here, so it's included in the result. x5 is included here, but not included here, so appearing in the result. x4 is included down, but not included up, so it's appearing in the result. This is an XOR operation. Okay, and also x3 and then x and x, they are removed together because they appear up and down. They are not included. And the last one is 1 because it appears down, not appearing up. I convert this to binary. x7 means 1. This is 1. x6 is 0 because it's not included, x5 is 1, x4 is 1, x3 is 1, x2 is 0, x only is 0, and this one is 1. Here, I can conclude that this is, I told you about this one, this is A, 1010, and 1011 is B, and 1100 is C. So 1011 is B. So this is B. And this is 1001, this is 8 plus 1, which is 9. This is B9. I take this B9 last and put it here in the output. Okay? This is long journey, long journey. If you miss multiplicating any simple operation, this will lead to very completely wrong answer. If you just, for example, if you forget x6, you put it x5, only just a change. This is not going to give you the exact result. So this is how to get all these operations, how to make the AES real example. This is a real example with the multiplication and on how to make these multiplications and how to use what we have learned in the previous lessons in our here in the exam, in the algorithms, how to use the mathematics in the algorithm. Now we get to the last parts of the lecture. This is an example. This is avalanche effect. This is avalanche effect of AES. We just change one bit in the input. Here, if you see here, we have the same thing, but here we just changed the bit, the first bit in the second. This is, for example, this is 0000, and this is 0000. I changed it to 0000 and 0000. This is 0001. I changed one bit only. One bit is changed. So the difference here is one bit. After that, we have 20 different bits. We have 85 different bits. And last, we have 58, not 85, 58 different bits. This is the avalanche effect, means that there is no relationship between the input and the output. And each stage is different too. So we get totally different output in each stage if we change it only one bit. And the avalanche effect in the key also, if we have a key, I change it single bit in the key and I get totally different output in each stage. That's why we need to make all these complex operations. And that's all for today. And thank you for listening to me today. For this is the most important algorithm in symmetric algorithm, which is advanced encryption standard. Do you have any questions?